All right. Chapter 14 is all about binomial theorem and sequences, arithmetic and geometric. But we will begin by talking about binomial theorem. So, binomial theorem is this essentially here. In binomial a plus b to the n, any of its terms will be this NCR times a n minus r br, where NCR is the factorial coefficient coming from Pascal's triangle, and r is the term number starting at 0. So that probably made absolutely zero sense. And that's perfectly okay, because all of this will start to make sense as we go through this problem 4 here. So the coefficient of the term containing a or a to the third power, not a3, a to the third power in the expansion of a minus 2b to the third, all to the 11th power. So first of all, how do we even go about starting this? Well, let's think for a minute about how these binomials even function, because that's a huge power right there. So when we begin with everything, I'm going to use this nonsense here to describe this. When we begin with everything, you'll notice that let's say we start at this n equals 5 here. We'll start at 5 for x, go down to 4, to 3, to 2, to 1, to 0. If we start it and we look at the y's, it goes from 0 to 1 to 2 to 3 to 4 to 5. So if you see, each time we decrease by 1 as we advance in the term by 1 for the first a value. Hence why the x got lower and started at the maximum n value, where n equals 5. And then each time we went a term number further, it decreased. Now, we don't count this first term as term 1. We count it as term 0, because otherwise this whole problem here would not make very much sense. So obviously, if we use this whole format here, ignoring the NCR for now, because that's some complicated stuff I'll get to later, if we go through this format here, we have a n minus r, so n here is 5, r would be 0 because it's the first term, so it would be 5 minus 0 is 5, so that's the power for a being the first term, x, which is 5. So at term 0, x is to the 5th power, and then this br here, r is to the 0th power, or it's r is 0 because it's the first term, so y to the 0th power is 1. And now you can work your way all the way back from that to get to there. So if we go to this next term, where r would be equal to 1, so the first term, r would be equal to 1, so we would go 5 minus 1 is 4, so x to the 4th, b to the first power, so y to the first power, 1. And then the NCR comes in and tells us that this equals 5, which has something to do with Pascal's triangle. And how it involves Pascal's triangle, I will tell you in a minute, but if you were to pause the video and take a look at all the coefficients of all of these, you'll realize it follows Pascal's triangle. And how Pascal's triangle works is that there's an infinite row of zeros that go here, 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 all the way through. And what you basically do is you take the two adjacents and add them up. So this 0 and this 1 would add up to this one. These two would add up to that one. And then these two adjacent ones would add up to the 2. These two would add up to 1s. These 2 to 3s, so on, all the way down. And then each row is relating to this n here with that n in binomial theorem. So I haven't even talked about the problem yet. So if we want to find a term containing a to the 3rd power in the expansion of this, if we followed this, we could help us find that. So we know that what we're trying to find here, I'm going to grab my orange. What we're trying to find is a term where we have a to the 3rd. Now, a to the 3rd, we want to be equal to a n minus r, and we want to find that r value. We know n is to the 11th power, so this is 11 here. So we're looking for what term? We are looking for the 8th term, which if we think about it in literal terms, it would be the 9th term out, because we count the first term as 0. But it's the 8th term according to this. So that means n is equal to 11, r is equal to 8. It's important to note this. because then we can solve in this format here. We can go NCR, so 11C8. There's another way to write this. The NCR, there's another way to write this being 11/8, where you don't put a dash and you just set the numbers on top of one another. And I prefer to write it this way. But I'm just telling you that that's a way you can write it. But because I have it all written here as NCR, I'm going to write it here as NCR. 11C8 multiplied by the a n minus r, so the first term being a n minus r, so 3, and then b to the r power. So if we wanted to go b to the r power, we would go 2b to the third to the r power, which is 8. There we go. So we now have the term without this factorial nonsense. So I'll talk about what that factorial nonsense is in a minute. And obviously we do have it because we have an a to the third, and that is what we want. So now let's talk about this factorial nonsense. So there's a very complicated way that this works out to be. I'll show you first how you get to it on your calculator, and then I will go and solve it without use of a calculator. You will go here to math, go click this side button to go to probability, find NCR. On calculators that aren't graphing calculators with special abilities, you will have to type your n number before clicking this button. But because we have here a nice calculator, we can do that first. So we will go 11 and then type 8, and then it'll give us this number 165. Now I will explain how it gives us this number 165, but really you would just plug it in for that 11C8 right there. So how you get that number 165 is you go like this. You would take all the factorials from 11, or you would take the factorial 11 down all the way. So you would go factorial 11 all the way 8 terms. So you would go 11 times 10 times 9 times 8 times 7 times 6, 2, 3, 4, 5, 6, times 5 times 4, all over the factorial of 8. 8 times 7 times 6 times 5 times 4 times 3 times 2. We don't need to involve that times 1. So here we have the factorial of 11 all the way out to 8 terms. And then we have the factorial of, or we have all the way out 8 numbers. And then we have the factorial of 8 right beneath it. So now it's a very good idea to write it out like this beginning with, because then you can just cancel. Cancel, 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 cancel. So now we have 11 times 10 times 9 over 3 times 2. So if we then were to plug that into our calculator, because that's way easier, 11 times 10 times 9 divided by 6 should give us 165. So that would be the mathematical way on how you could solve this by using those factorial terms. So if we had an NCR, let's just say, of 5C3, we would go 5 times 4 times 3. We wouldn't go times 2 because we only need to go out 3 terms, judging by that 3. Then we'll go 3 times 2 times 1. We don't need to use the times 1, so we'll take out these 3's, divide that out. That's equal to 10. And then if we notice what n equals 5 on 3 is, so if we go to n equals 5 on our Pascal's triangle down here, n equals 5, the third term out where the first one starts at 0, so 0, 1, 2, 3 is equal to 10. And we do see that is equal to 10. And that's how that works. And why we have to divide that same factorial out is to ignore all of the numbers that would be repeats. So for instance, let's say before I solve this problem, let's say if we wanted to make all the different pairs of the letters A, B, C, D, and E. So we would pair A, B, A, C, A, D, A, E. We would then go like this. We would go B, A, B, C, B, D, B, E. We would go C, D, or no, C, A, C, B, C, D, C, E, D, A, D, B, D, C, D, E, E, A, E, B, E, C, E, D. That would be all the possible pairs, and that would actually be the other term here, which is NPR, which would give us all possible. But NCR is what we're trying to do here. So then NCR would eliminate all of the repeats. So that would mean we wouldn't have a BA. So here we wouldn't have a BA because we only need one AB. AC, CA eliminates, AD, DA eliminates, AE, EA eliminates. Now BC, CB eliminates, DB and BD eliminate, BE and EB eliminate. So now BD, CD, DC eliminate, CE, EC eliminate, and then now CE or DE and ED eliminate. So now we are left with only this 1, 2, 3, 4. So that would be 10 there. That would be 10, and we've eliminated 10 others. So that's why you would divide that out, because if you notice, that's actually divided by 2. So what we just did there was the NCR 5C3 or 5C2, which would leave us instead with that 5, 4, 3 divided by 2. So we would, or no, this 5, 4 divided by 2, because we're left with a total of 20 divided by 2 is 10. And that's just a physical demonstration of how this cancellation stuff works. And using those factorials, that's how you do it. So you would take, again, just to recap, the factorial of 11 minus the factorial of 3, because that would mean that we are excluding the other terms, and then to the factorial of 8. So how this factorial of 3 comes in is just making it only go back 8 terms. So that would be the mathematical form of how you would do this. You just need to know what a factorial is and how it works. So we said that this is equal to 165. So we would have 165 a to the third times 2b to the third times 8. So 2 to the 8th power, big number time, 256. B to the 256b to the 24th. And then it only wants us to do the coefficient, so we can kind of ignore all the variables from this point on and just multiply 165 by 256, which is some huge number, 42,240. So we only want to know the coefficient, so 42,240. This will be our answer, but if it were asking for the full term, it would be 42,240 times a to the third, b to the 24th. Oh, there we go. Number 4 is done. The hardest part is explaining how that math works. Okay. Luckily that all worked out. I'm going to pause the video now before something corrupts the video footage, and then we'll come back for number 5. Okay, here we go. Big, long nonsense. Absolute nonsense. Expand all of that. So, oh my God. If we know that each of the terms can be equal to that, we can set every term equal to that, where we specify what each NCR is. So we will start here by going like this. Oh, hello, AirPods did the thing where they tell you you're low battery. So give me a minute while I plug one of them in. Hopefully it doesn't die on me mid-recording. That would be very, very bad. Okay. So we will note every term in terms of the NCR A minus RBR. So we will go like this. NCR. You know what? I'm going to erase that and write it a little smaller because I'm going to need space. So NCR, our total N, is equal to 5. And then R varies. So I'm going to say R is variable. So R can actually be any number between 0 and 5. So it can be any number between 0 and 5, just depending on which term we're talking about. So let's go like this. We'll go 5C0, 5C0, and then we'll have 3x cubed, n minus r, so 5 minus 0, times b y third to the 5th power. Okay. Verifying that this all checks out. Yes, it does. Oh no, this is R0. I was wondering why that was working, or that wasn't working. Okay, and then we'll have plus 5c1, 3x cubed, and this is going to be 4, because this one here is 5. So this one now y cubed is 1, plus, you see how this is going to get long and done? Plus 5c2, 3x cubed, or 3x squared, all cubed, y there, that nonsense, plus, and then I'm going to have it carry over to here by using those dots. 5c3, 3x squared. If you don't understand what I'm doing, please recap on my number 4. And also, if you don't know how I got the n's and r's, please recap on the number 4 as well. We will then go 3x squared, 4, y cubed, 3, right? Yeah. Oh no, this is supposed to continue decreasing. So that's 2, and then that's 3. There we go. Plus, I was wondering why that was looking weird. 5c4, 3x squared, 1, y cubed, 4, plus 5c5, 3x squared, 0, y cubed, 5th power. Whew, we wrote out the whole thing and didn't need to use 3 lines. So now let's go and do the whole thing. Now, I already showed how to do the factorial form earlier, so I'm going to use Pascal's triangle to just give me what each of these 5C nonsenses are. So, and I will guarantee you, doing factorial form helps when you're doing a singular problem and your n is way bigger than Pascal's triangle will let you, but just draw out Pascal's triangle and understand that it's the same thing as using the factorial form if you have a number that's easy to write Pascal's triangle with. Okay, plugging in the other AirPod back in so that way it doesn't die on me mid-recording. Please work. Please work. Ah, it worked. Unplugging the other one. Please, please, please don't disconnect. Don't disconnect. Don't disconnect. Oh, we're good. Okay. I can see the sound bars on the app I'm using, so we're good. Okay. So now let's simplify everything out, and I'm going to use Pascal's triangle again. So just note for a second that if you have a 0 here or you have the same numbers here, they'll both be equal to 1. That's just an always fact. You can't have the second number be bigger than the first number in NCR. That's also impossible. So let's go about solving this whole thing. So we know that those will be 1, so we can kind of cross those out. We know that these will be 1, so we can cross out the zeros. We know that these will be 1, so we can kind of just erase them. And then now we'll get into the whole nonsense. So we'll go 3x squared to the 5th power, so 3 to the 5th power, and then x to the 10th. And then we'll go plus 5c1, 4n to the 5th is 5. 5 times 3 to the 4th power, x to the 8th power. Please tell me it's still working. Yes, it is. Good. And then we'll go y to the 3rd power, and then we'll go plus 10. So 10, 3 to the 3rd power, x to the 6th power, y to the 6th power. Okay, and then we'll go plus. Luckily, I have this open space here on the side where if I need to, I can continue going that way. Plus 10, 3 to the 2nd power, x to the 4th power, times y to the 9th power plus 5, 3x to the 2nd power, y to the 12th power plus y to the, this is a 5, not a 3 to the 15th power, or y to the 15th power. Oh, let's keep going. We're close now. 3 to the 5th power, 3 to the 5th power. Do the whole thing. It's 243. 243 x to the 10th plus, so 5 times 3 to the 4th power is 405 x to the 8th y to the 3rd plus 10 times 3 to the 3rd power is 270 x to the 6th y to the 6th. I probably could have easily done that in my head, but I don't want to even try. 90 x to the 4th. As I say that, I proceed to do something in my head. 90 x to the 4th y to the 9th plus 15x to the 2nd y to the 12th plus y to the 15th. That is the entire thing. Kill me now. Woo! Okay. That is the entire expansion. I hate everything. Okay. I actually hate those with a passion, and I'm very glad that there's only one of them here. If there was multiple, I would not have even done it. Okay. Number 6. Determine, oh, here we go. So now we're getting into arithmetic sequence stuff. So I'm going to end the video and then play the video again, but with different stuff over here. We will begin sequences with a custom problem. So this is saying this is an arithmetic sequence and to find the 4th term. So already we have natural log of 9, natural log of 3, so on, which seems daunting because it's logarithms, which takes us way back, but I promise you it's not that bad as long as you remember one rule of logarithms. So how an arithmetic sequence works, first of all, is we have a number which is equal to the first term of the sequence plus the recursive of that number time, or plus the common difference times how many we need to go by. So let's say our thing was like 1, 3, 5, 7, so on. The arithmetic sequence for this in AN form would be 1 plus D, and then our D would be our common difference, which means it would be 2, because our common difference is how much we need to add to get there. And if you'll notice, it would be add 2, add 2, add 2, horrible 2 right there. So 2, and then n minus 1 is just how many terms we need to go by. But notice that it's n minus 1 because we already count the first term. So it's just n minus 1 to say it's that many terms back from the number 1. So if we're trying to do the second term here, this n be equal to 2, which means it's 1 past 1. So it would be 1 plus 2. So 1 past the first term. So now we're going to step it up quite a bit with this arithmetic sequence, finding the 4th term. So we know that there must be some addition we do to get from there to there. Well, this revolves around one rule of logarithms. I encourage you to pause the video and try to think of it yourself before you go on to this one. All right. The rule of logarithms that we must follow for this is r logarithm of x is equal to logarithm of x to the r power. So multiplying a logarithm is equal to putting the logarithm to that power, where we have this here. So in other words, logarithm 3 squared, comma, logarithm 3 to the 1st, comma, so on, is our arithmetic sequence, which means our arithmetic sequence is actually 2ln to the 3rd, and then ln to the 3rd, so on, which means that our subtraction each time is 1 ln to the 3rd. So our common difference is ln to the 3rd. And we can verify this by going onto our calculator and doing this. So natural log of 9 is equal to that. Natural log of 3 is equal to that. Natural log of 9 minus natural log of 3 should equal the previous answer if this is indeed true. And yes, it does. So now that we know our common difference, we need to find that fourth term. So we'll start with our first one. So, oh, that's the wrong color. Where'd my color go? There it is. So we're looking for the fourth term. A to the fourth is equal to 2ln to the third plus d being ln to the third times n minus 1, so that would be 3 because we're looking for the fourth term, which means n is equal to 4. So multiply that by that, we get a to the fourth, and this is actually subtraction, so it would be minus that. So that would give us 2ln to the third minus 3ln to the third would give us a to the fourth is equal to negative ln to the third. And that's just to give a recap on how arithmetic sequences work. And also, by the way, this was drawn almost exactly from a test I took on my final. And that's just because I literally remembered the problem. So what's the teacher going to do about that? Nothing. They can't do anything. Okay, now we'll go on to number 6. Sum of first 20 terms in arithmetic sequence, which I'll abbreviate with arithsec, in which where A1 is equal to 8 and A20 is equal to 43 over 2. Okay, so what's very nice about this problem is that we have an equation that perfectly models this already. Our equation is the sum of, for arithmetic, which is in this box here, Sn is equal to n divided by 2 times the first term plus the term that you're going to. So if we want to do S20, we would go S20 is equal to 20 divided by 2 times the first term, 8, plus the term at 20, which is 43 over 2. And then now you would literally just plug this into your calculator. So 10 times 8 plus 43 divided by 2 is equal to 295. And that is our answer. S20 is equal to 295. Simple. Okay, now we will go to number 7. Where are we at in time? 6 minutes, perfect. So 7 is different. It says sum of infinite geometric sequence. Sum of infinite geometric sequence, 7, 10, 7 over 100, 7 over 1,000, so on. Okay. And this is a sum of, so these aren't actually commas, they're actually plus signs. So we have an infinite geometric series here where what seems to change is how big the bottom number is. The top number does not change. So if the top number doesn't change, we can use the recursive formula of the geometric sequence to solve for our common ratio, which is how much it divides by each time, how much it divides or multiplies. So basically what the recursive formula for both arithmetic and geometric, it says that for arithmetic, it's the number before n, so the number right before the number we're talking about, plus the common difference is equal to the number we're talking about. And then geometric, it says the number right before the number we're talking about times our common ratio is equal to the number we're talking about. So the number we're talking about in this instance, let's say, is 7 over 100 is equal to something times the number right before it. So what would we have to multiply this by to equal that? Well, we can just set up a simple proportion for that. 7 over 100 is equal to 7r over 10. Divide both sides by 7, and then we would get, if we divide both sides by 7 and then multiply both sides by 10, so we would go 7 over 10, 7 over 10. We would get 49 over some huge nonsense like that is equal to, oh no, this, I did not do that right. I'm going to say, excuse me for a minute. I was wondering why that wasn't checking out. These two sevens would cancel. This 0 would cancel, and that would cancel. So we would get 1 over 10 is equal to r. So r is equal to 1 over 10. So that is our common ratio. Also, I just realized I was doing most of that math in green. So 1 over 10 is equal to r, which is obvious because each time this goes up by 1 power of 10. So we would be multiplying it by 1 over 10. And my knee hurts, so I'm constantly changing the position I'm in. So now what we can do is try to solve for this. So we need to find the sum of this infinite geometric sequence. The difference between our finite and infinite geometric sequence sum of equations here is that the finite one will go to a finite number. It has to, because our ratio will blow up to infinity because it's bigger than 1. In this instance, it's not bigger than 1. It's between 0 and 1, or it's actually not 0, between 0 and 1, and then also between 0 and negative 1, just because that's how infinite geometric sequences work. So that means that we can literally have n blow up to infinity, and it will still settle on a single number. And then the perfect example of this would be if we are trying to paint a wall, and we decide that we are going to paint half of it a day. So if we decide to paint half of it a day, we would have this half done on day 1, this half done on day 2, and when I say half of it a day, I mean half of the remaining portion left. Half of this on day 3, day 4, day 5, day 6, day 7, day 8, and then by the time we get to day infinity, we have painted one total wall. So that would mean that this infinite geometric sequence would fall on 1. So now here, this one has the difference of this being Sn is equal to, and this Sn should actually be just S infinity. So I'm going to really quickly change that here to S infinity. S infinity is equal to the first term, so 7 over 10, divided by 1 minus 1 over 10. So it would be S infinity is equal to 7 over 10 times the reciprocal of 1 minus 1 over 10. So 1 minus 1 over 10 is 9 over 10, so this would be 10 over 9. These two 10s cancel out. So then we get S infinity is equal to 7 over 9. So that's what the sum of that infinite geometric sequence is equal to. Okay? Now, number 8 states a sequence is defined recursively as follows, okay? So A1 is equal to 1, A2 is equal to 1, and then AN is equal to, this is about to get very complicated, but I'm going to decode it very quickly. AN minus 1, where every time you see this n minus 1 or n minus 2 or n minus or n plus, you have to think of it the number before or after, or this many before or this many after the number in question. That number squared plus a n minus 2, so the number 2 before the number in question, for all for all times where n is greater than or equal to 3. So this rule will only work when n is greater than or equal to 3. But this is still nonetheless a sequence because there is a pattern. So determine the fourth and fifth terms of this sequence. So a to the fourth is equal to something, a to the fifth is equal to something. Well, we have to purposely go along and do it every single time. So let's first solve for a to the third. So a to the third is equal to a to the second squared plus a to the first, just a to the first, not squared. I don't know why I wrote that. And this one will work because n is greater than or equal to 3, so this will perfectly work. So a to the third is equal to a to the second, which it gives us squared, which is 1 squared, plus a n minus 2, which is 1, so a to the third is equal to 2. Okay, now we need to solve for a to the fourth. A to the fourth is equal to a to the third squared plus a to the second. So a to the fourth is equal to a to the third squared. So that would be 2 squared, so 4 plus a to the second, which is 1, so that would be 5. So that's one part of our answer. A to the fifth is equal to a to the fourth squared plus a to the third. A to the fifth is equal to a to the fourth squared, so that's 25, plus a to the third, which is 2. So a to the fifth is equal to 27. And that's it there. This just seems super complicated. But instead of reading this as a n minus 1, because that confuses your brain, read it as this is the number before that number. This is the number 2 before that number. And that will make it a lot easier, because then when you go to solve for number 3, you'll do that. And then what you'll realize is if you try to go straight to a to the fourth or a to the fifth, you'll realize that you need a to the third in your problem to solve for it, which you don't know yet. So you'll have to go and do a to the third. Okay? Now, let's do number 9. Number 9 says, in a certain geometric sequence, so a to the third is equal to 4, and a to the fifth is equal to 10. This is geometric. Find the eighth term, given that the common ratio is negative. A to the eighth term is equal to something. R is less than 0. Ooh, we got some complicated stuff going on here. So first, let's just set up a bunch of equations that we know will be true, even if they involve a ton of variables. So we know a to the third. So a to the third is equal to a to the first times r. So the third, so that would be 3 minus 1, so 2, so r squared. So we know that 4 is equal to a to the first times r squared. So then we could also do a to the fifth. So a to the fifth is equal to a to the first times r to the fourth power, because that would be 5 minus 1. And then we can plug in a to the fifth as 10. And then let's solve for a to the first for both of these. We'll go 4 divided by r to the second is equal to a to the first. And then 10 divided by r to the fourth is equal to a to the first. And then we'll set these equal to one another since we've now solved for both instances of a to the first. So 4 r to the second is equal to 10 r to the fourth. Let's multiply everything by r to the fourth. So that way we can get everything out of our denominators. So we'll have 4 r to the second is equal to 10. Divide both by 4. So r to the second is equal to 5 over 2. And then we know it's a negative number. So r is equal to negative rad 10 over 2. And that's just me simplifying it immediately for that radical. So we know that this is our common ratio, and we need to know a to the eighth. So now let's plug in. A to the eighth is equal to a to the first times r to the 7th. So first what we're going to do is we're going to use these equations right here that we got to solve for a to the first. So 4, and then we know this is negative rad 10 over 2 squared is equal to a to the first. So let's just plug this into our calculator here. So 4, so negative rad 10 over 2, all of this squared is equal to 1.6. So 8 over 5. 8 to the first is equal to, did I say 1 over 5? I meant this, yeah, 8 over 5. That's what I said. Okay, so now we'll plug it in for this all nonsense here. 8 to the 8th is equal to 8 to the first. 8 over 5 times negative rad 10 over 2 to the 7th power. And then we would go ahead and solve for that. 8 to the 8th is equal to, and then let's try to solve this where we get it as exact as we can. So we will have negative 8, and then we would have negative 8 times rad 10 to the 7th over 10. So a to the 8th is equal to, so rad 10 to the 6th power, firstly, is 10 or 1,000. So it would be negative 8,000 rad 10 over 10. So then a to the 8th is equal to negative 800 rad 10. And let's write that a bit nicer. There we go. And that is our answer for a to the 8th during this geometric sequence. I'll pause the video and then we'll get to number 10. All right, number 10 asks us, what is the 20th term in this arithmetic sequence? Negative 61, negative 46, negative 31, so on. So first, arithmetic sequence. So we know that there's going to be a common difference between each of these. We can use the recursive formula here to solve for that. So negative 46 is equal to d plus negative 61. So it would be d minus 61. And then we would go add the 61 to both sides. So 61, so negative 46 plus 61 is equal to 15. I don't know why I couldn't do that in my head. 15, let's just verify that. If we add it to that, it does equal that number. So that does check out as our common difference. We know our A1 is equal to negative 61. So that's cool. And then now we'll go a to the 20th is equal to a to the a first, which is negative 61 plus 15. So our common difference, n, we're going to 20, minus 1 is 19. So we'll go negative 61 plus 15 times 19 is equal to 224. So a to the 20th is equal to 224. Perfect. And now that's me finishing the lesson plan I have, but I'm going to talk one more small thing about how sigma notation works and finite series works. So I'm going to do 2 more examples. So in this example, we have the sigma notation. Oh, I'm using the wrong color. So we want to solve where we are given a sigma notation of, let's say, 3, and then, no, let's say 6, 2, n is equal to 2, where we have our equation is 3n plus 1, and then we are asked to solve that. First of all, how do we even read that? Look at it. It's nonsense. So how we read it, based on what we have here, is this is what we're going to start on. This is the number we're going to start on. This is the number we're going to end on. this is the repeating thing that we're going to do. So, in other words, this here is equal to a to the second plus a to the third plus a to the fourth plus a to the fifth plus a to the sixth. So let's just go ahead and do it. So 3, 2 plus 1 plus 3, 3 plus 1 plus 3, 4 plus 1 plus 3, 5 plus 1 plus 3, 6 plus 1. And we'll go ahead and solve for that. So this here is 1, 2, 3, 4, 5 ones. So 5 plus 6 plus 9 plus 12 plus 15 plus 18. So then 15 plus 27. You know what? I don't even care. I don't even want to do this in my head. 5 plus 6 plus 9 plus 12 plus 15 plus 18 is 65. So that's all equal to 65. And that's how you read sigma notation. Okay? Now, let's do one more example where we do a finite series. So let's say our geometric series is 1, 2, 4, 8, 16. That's our geometric series. And then we want to find sum up to 15th term. So we want to find the sum up to the 15th terms. This is our finite series. We have to stop at a finite number because our common ratio is larger than 1 or smaller than -1. So basically, it won't peter out to nothing. It will go to infinity if you let it go to infinity. So we have, wrong color again. S20 is equal to, and then let's just copy our equation. The first number is 1, so we don't need to do much. We have 1 minus r to the nth power. We need to know our r. This multiplies by 2 every time, so r is equal to 2. So 2 to the 20th power, all over 1 minus 2. Okay, now let's find our sum from here. Let's just plug it into our calculator. 1 minus 2 to the 20th power plus 1 minus 2 is equal to that huge monstrosity. S to the 20th is equal to 1,048,575. And then that's a finite sum. There we go. Now we've talked about everything involving these, and I can rest with all of pre-calc done for what we did this year at least.